Thank you very much. Let's see if I can make this machine work. Just quickly tell you what we're going to talk about today. I'm going to talk twice. The first time with my marketing hat on, so you can ignore what I say, and that'll be a little introduction. Then Al will talk about the ARM6, and I'll come back on with a technical hat on and talk about the ARM610 and our future directions, and at the end of that we'll take questions. Okay, so a little introduction. I'm not going to do too much on the company and things like that, but I think it's worth knowing where we came from to understand why the ARM architecture is like it is. We all started back in 1983 in a company called Acorn, which is a bit like a UK version of the Apple. We grew to be about 70% of the education market, but never broke outside of the UK, so never got too big. And back in '83, we'd made lots of money. We'd sold 1 million machines based on the 6502, like yourselves, and we're looking around to develop our next generation products. And all of those machines were dual processor machines. They had the capability to be upgraded with another processor. And we investigated lots of different families, Motorola, Intel, National Semi, and were never really happy with any of the chips we chose. We started going with the 16032, but that ran into serious problems. It was a RISC chip that they couldn't make. It was late. We were looking for a processor that didn't have all the disadvantages of a big RISC chip. And so we were used to doing I/O all in software. We didn't like DMA channels. We wanted low interrupt latency. And the 16032 family seemed to solve some of the problems, but basically it was a big, slow, expensive system. And around that time, the owner of the company, a man called Herman Hauser, came back from America and said, well, over there, all the research labs are talking about RISC chips. Why don't we build a RISC chip? So we sat around and kind of said, OK, we'll build a RISC chip. And in those days, it was called the Acorn RISC machine. We've since kind of subtly changed the name to Advanced RISC machines. So we started development in '83. And we're blissfully ignorant of what the rest of the world was doing with RISC chips. We were basically designing a replacement for the 6502. The rest of the world seemed to be saying, hey, RISC means we can build the fastest processors around, whereas we were interested in building cheap computers for home and education. So we kept all the things we liked about the 6502 and built on that. We licensed the technology back to VLSI in '86, and they've been selling the chips, and I believe they sold several into Apple. We never really knew what you were doing with it. We got strange requests for trick compilers for big endian arms, which we'd never built and we weren't quite sure about, but we kind of shipped it out because it seemed fun. Nothing ever came of that, so we often wondered what had actually happened. Now I know some of the stories, but I don't think I should tell them. In 1990, we were sitting around, and we'd been bought by a company called Olivetti by then. And several Italians in sharp suits had come over to Acorn and said, we like the technology, we can't really afford to support you guys, you're all paid too much, can't we spin you out into a separate company? And they tried several times to find someone to spin us out with, and that didn't come to anything. And one day the phone goes, and it's Larry Tesler saying, we like your product, however, we'd like a few technical changes. We'd like it to go faster. We want a full 32-bit address bus. It's got to take less power, and you've got 9 months to do it. How do you feel about it? So we said, sure, we can do that, no problem. I even looked him in the eyes when I said it. And so Advanced RISC Machines got spun out as a separate company, and we started off in offices inside Acorn. And in the first 9 months, we moved out from Acorn, not into a garage, but into a 17th century barn in a village just outside Cambridge. And we started the product development of the ARM6 family, the 600 and the 610, which I'll go on and talk about in a minute. In '91, we launched the ARM6 family. We opened the ARM office in Los Gatos, and that's Tim at the back. In '91, we actually got you to say that you might possibly use ARM in some product sometime. The rumors seem to be leaking out a bit better, so that seems to be becoming a little clearer what you may or may not be doing with it. And then in 1992, we licensed GEC Plessey Semiconductors, who are a UK company to make the chips. We design things, we don't make anything. So we rely on our licensees to actually make silicon. This has gone to sleep. Why is the ARM different? Well, we designed it as a 6502 replacement, and what we came out with was a really small die. So ARM6 is less than quarter the size of the other comparable RISC processors. Now, that means you've got something that's small, so you can get it cheap, or you can do high levels of integration. You can build ARM6 as an ASIC, put a whole load of other logic on there, and still end up with a chip that's cheaper than competing RISCs. The other reason that we think you liked it is power consumption. We kind of invented a new metric for measuring things. MIPS is getting dull, so we've gone for MIPS per milliamp. Okay, I'm a marketing man, I've got to find a slide that kind of really makes the ARM stand out. But it's important for battery-operated products, that's what counts. Now, okay, you have to get the system power down, but getting a lot of power for a few milliamps really, really matters. And we achieved that because in the ARM design, we threw out those nice frills that made it go 10% faster here and 5% faster there, and we've kept something that's small and simple. And as a result, really good power consumption. Now, hardware is the easy bit. Doing software development is often the really tricky part. So what we've developed for embedded control applications is an integrated software development environment. We took with us from Acorn the C compiler that had been used to build their Unix product, so sort of industrial strength C compiler, PCC or ANSI C, and the assembler, which I guess is slightly embarrassing. I mean, the guy that designed the ARM instruction set was a 6502 freak who wrote BASIC interpreters and wanted to write a BASIC interpreter in handcrafted assembler. The rest of the company was using Modular 2 and wanted a processor for high-level language. So we got a compromise between what would you use as a target for a Modular 2 or a C compiler, and what do you actually get if you want to sit down and handcraft it. So unlike most RISC chips, it was actually designed to be programmed by humans as well as by compilers. And if you're doing small embedded applications, then the ability to get in there and write good optimized code is very important. And one of the things that comes out of that is good code density. In order to do product development, we've also developed a software simulator of the ARM that allows you to do benchmarking of critical code before you've ever actually built any hardware. And the software simulator runs at about half a MIP. Now, half a MIP on a Spark station is tolerable performance for actually debugging an application, and that gives you profiling, cycle counting. You can really look at the critical code and optimize it. And in a nice development environment on a big machine, now use Macs. On a Mac, you can do all of this. So this stuff runs on Mac, PC, and SunSpark. And the development environment allows you to develop your application on your host and port it across to your target. And that target could be a software simulation, development card that's some out the back, or your own target hardware. And to make that port of the application easy, the hardware has a remote debug interface that actually allows you to split your ANSI C library between your host and your target. So you can start off developing software on your host using all the facilities of your host C library. You can then move the application, and the bits that you don't really want in your final system but are useful for debugging, you can leave back on the host, and so the C library can be split between what runs on your target and what runs on your host. Hardware development, not too hard. You can take your workstation, do a schematic capture of your ASIC, bringing in standard libraries for all your standard features, a simulation model of the ARM. It all integrates in with the software development environment, so you can still use the same compilers and debuggers. Get your design right, push the button, and your vendor will tell you that within mere moments you'll have an ASIC dropping out the bottom. Now, you had a PowerPC presentation the other day. It's worth pointing out that we in no way compete with things like the PowerPC. PowerPC comes from workstations and crossover into the desktop world. ARM is all about the crossover between the desktop PC and consumer applications, where you want things that are small, cheap, and low power. And we've never claimed to be the fastest RISC processor in the world. We're just one of the cheapest and one of the most power efficient. Just a little overview of the current family of processor products. It's the ARM6 family. Now, some of you might be familiar with the Acorn past, where we had ARM2 and ARM3, and might wonder, why have we now gone to ARM6? Well, I think I can blame Larry for this. In all of our development programs, we had ARM4 as our next processor family. It made a lot of sense to us. Larry said, this is dangerous. You're locked into the 286, 386, 486, Motorola 030, 040, maybe 050. If they release a new product, the 586, you're going to have to come out with the ARM5. We should get out of this race on numbers and leapfrog to ARM6. I'm sort of have a little underground campaign to try and backfill some products into 4 and 5 so we get a nice family flow, but we're at ARM6. And Larry had another idea, which was what we've got is a processor core that's good for ASIC design. That's the fundamental basis of our product. That's the ARM6. But what happens when you want to turn that into a standalone CPU? Well, you add a 0 on the end. And for a 0, it costs you a bit of money. You get a pad ring and a JTAG tap controller. Then if you want things like caches in MMU, you have to buy another 0, and that becomes the 600. And this sort of, the more money you spend, the more zeros you get. And the ones on there are just kind of cost-reduced versions, the 61 and the 610. And Al's going to go over some of the ARM6 architecture, and then I'll come back and talk about the ARM610. So hopefully that's the ARM6 architecture. I'll hand over to Al, who really understands how that works.
Thank you. Good afternoon, ladies and gentlemen. Yes, I'd like to talk to you about ARM6 and its architecture. ARM6 is the core of all the ARM products. We add boundary scan, pads, caches, etc. to that, and that's how we build up the more powerful members. But the heart of it is the ARM core, and that's based on RISC principles. So it has all the things you would expect from a RISC. It has an instruction pipeline, which in ARM's case is 3 instructions long. All the instructions are exactly 32 bits long, and it's based on a load store architecture. So you read data from the memory into the registers, work on them there, and store the results back again. But ARM is not a pure RISC. We weren't driven by any of the ideological goals to get thousands of registers with register windows, to get everything down to the shortest possible cycle time by splitting things up. Instead, we aimed for something that was very efficient in terms of instruction density, was easy to program, and very small. So it has a few interesting things added to it. For instance, block data transfer instructions. It allows you to transfer many registers between memory and the register bank at one time using a single instruction. It has a parallel barrel shifter. So instead of just taking the operand straight out of the register bank and using them, you can pass one of them through a barrel shifter and shift or rotate it by any amount with no extra cycle overhead. All the instructions are conditional. That comes in very handy later on because you can eliminate short forward branches. And all this leads up to, with a rich set of addressing modes for data transfer, very important if you've got to get data to and from memory, that you're able to do that freely and have a good means of actually specifying the address. All of this leads to very good code density, which is 30% better, about 70% of the size of a SPARC or a MIPS RISC processor, and round about the same size as something you're probably more familiar with, 68030. I like to go around a block diagram. This is a rather simplified block diagram of ARM6, but shows the main bits and pieces. If we start on the left-hand side, this is the data path section of it, and on the right-hand side, sitting in rather innocent-looking rectangles, is all the messy control logic. In the middle of the data path is a register bank. That contains the ARM registers, of which you can see 16 visible registers at any one time. One of those registers, R15, always holds the current value of the program counter. There are a few other special bits and pieces that some of the top registers are used for, but essentially you have 14 registers at your beck and call to play around with. It has 2 read ports and 1 write port, so in a typical data processing instruction you read 2 operands, pass them through the ALU and write the result back to the registers. One of the operands goes straight to the ALU, but the other one passes through this barrel shifter. And that's the device which allows you to shift or rotate that second operand by any amount. You can specify the type of shift and the shift amount in the instruction, or you can use a third register to actually specify how much you want to shift it by. That is a very powerful way of of scaling one of your operands, and is also used to generate immediate operands for use in some of the data processing instructions. The ALU at the bottom is a fairly standard device. It has arithmetic and logical operations. Nothing particularly interesting about that other than the fact that it allows you to conditionally set the flags at the end of the operation. Instead of always updating the flags, there's a bit in all of the data processing instructions which allows you to nominate whether or not you want the flags altered as a result of performing that operation. That comes in very handy when you do the conditional code assembly of the actual instructions, because you don't have to upset the flags as you go through. Down at the bottom is the data I/O block. There's a 32-bit data bus that ARM connects to memory with, and that's used to fetch all instructions and transfer all data across. So it's not a Harvard architecture where you need 2 caches or multiple ports to memory. It's very easy to design into simple systems. Again, that's why ARM was originally designed, to bolt into simple systems. And at the top is an address generator which contains an incrementer that's used to increment the program counter as you sequentially fetch instructions from memory. Now on the left-hand side at the top is the clock block. ARM uses a single clock to specify all its timing, and the clock is stretchable. There's a maximum speed specified but no minimum. You can stop the clock in either phase and the part will only consume leakage current, a matter of microamps. So it's ideal for portable equipment where you want to put the processor to sleep. If you want it to sleep, just stop its clock. The clock is also variable, and the power it consumes is directly proportional to the frequency you run it at. So if you're not looking for the maximum performance in your application, just run the processor slower, it'll take less power. At the memory interface, there's a couple of fairly standard signals, read, write, and byte word, which specify the type of data transfer you're doing. The next 2 signals are more interesting. They're both pipelined by half a cycle. That allows you to predict what ARM is going to do next cycle. The first one, memory request, tells you whether or not ARM will be using memory in the next cycle. And the second one, sequential access, predicts whether the location that ARM will access is 1 word further on from the current one. Those were originally put in there to handle DRAMs, where if you're running in page mode in DRAMs, you really want to know up front whether the next cycle is going to be in the same page as the current one, or whether you've got to strobe in a whole new row and column address. That also comes in very useful, as we'll see later on, in 610 to save power. There's also an abort signal into ARM. Any of the data access instructions you can abort, and ARM will then take an exception. You can fix up whatever caused the abort, restart the instruction, and continue on your way. So you can add an MMU to this and have a full virtual memory system. The interrupt blocks, I've actually cheated here. There are 2 interrupts, but I only drew 1 because the slide was getting busy. One of the main things about ARM was we wanted very fast interrupt response. So when we designed it, we made sure that you could get into your routine with all relevant states saved in the minimum possible time. ARM achieves this by having an extra bank of registers. When you see an interrupt, it's first of all synchronized to the incoming clock. ARM will then finish the current instruction and then immediately jump to the start of your exception handler routine, and at the same time switch in a new bank of registers. So you don't have to worry about pushing things to the stack, which takes time. It's automatically saved for you. And that all leads to a fact that you can actually get into your interrupt routine in less than 1 microsecond when running at 25 megahertz. Screen's gone to sleep again. I hope you haven't. Somebody hasn't, thank you. Block data transfer. There are a couple of instructions, load and store multiple, which allow you to transfer many registers at once between the register bank and memory. Each register you transfer takes one cycle, but they don't have to be contiguous. So in this example, I'm going to transfer register 0, 5, 6, 7, and 14, and it'll still only take me 5 cycles to transfer those, even though there are large gaps between them. This allows you to do very efficient block moves because you can suck a lot of data from memory into the register bank and then spit it back out again. But it's also extremely important for procedure entry and exit. When you want to push things on the stack, you can use a single instruction to push as many of the registers as you want onto the stack, and at the end you can recover them all with another single instruction. Conditional instructions. Every ARM instruction is conditional, so there's a 4 bits at the top of the instruction which specifies a condition code. There are 16 possible conditions, for example, equal, not equal to, less than, greater than, and always, a very important one since a lot of instructions you always want to execute. When the instruction comes to the execute stage of the pipeline, you compare that condition with the current flags. If those match, then you go ahead and execute the instruction. If they don't, then you skip it. Because the flags are optionally altered by data processing operations, that becomes very useful for doing interesting little, although slightly contrived examples such as this one. Here we have a greatest common divisor routine. At the top is the C for this. It's a while loop which embeds an if-then-else statement, and that'll actually compile down to 4 instructions. They're color-coded here, but you can program it in black and white. The root of the instruction is shown in green. The condition codes are shown in red, and the S I'll explain in a moment. The first instruction is a compare, so it compares the values in the 2 registers A and B, and the S on the end of it tells you that you actually want to set the condition code flags as a result of doing that. Important if you're doing comparison, you actually want to update the flags as a result. The next instruction checks the outcome of that, and if A was less than B, it'll subtract A from B. If it wasn't, that instruction will be skipped. The second instruction will be executed if A was greater than B. And the final instruction is a branch back to the beginning of the loop, which we will take unless the 2 numbers are equal. So with 4 instructions, we can do that C construct. So to summarize ARM6, it's a 32-bit RISC architecture, but it's small and beautifully formed. So it's only 33,494, fairly accurate, transistors, and it leads to a very small die. I'm used to millimeters because I'm European, but if you work in mils, the numbers are there too. It's 11.1 square millimeters, a very small die, so you can build an ASIC with the ARM in a corner and lots of other stuff around the outside. Indeed, that's essentially how the ARM 610 is done. It's a fully static design, so you can stop the clocks and it will consume only leakage current, less than 10 microamps, ideal for portable equipment. Very low power consumption, 1.5 milliamps per megahertz. Again, a direct result of not having an awful lot of logic in there thrashing around. So that's directly proportional to frequency. If you don't need the performance at 25 megahertz, run it at 12.5 and only take half the power. Having said that, it's still a very high performance part. 30,000 dry stones at 25 megahertz, and that's not with a trick compiler. And a very low interrupt latency. Less than 1 microsecond at 25 megahertz. So you can throw away a lot of those buffers that you have in your DMA equipment and simply do all the data transfer with software, because you really can get there and service the interrupt in time. And finally, it's big or little endian. ARM was originally little endian. A rather large customer requested that it become big endian. I can't really imagine why. So we've done it, and it's fully selectable, will work in either mode. Okay, I would now like to hand back to Mike with his different hat on. This is an engineering hat, so you can believe him.
Thank you, Al. Yeah, I guess in a few months after having had my marketing title for that long, I won't be able to do technical presentations anymore. Okay, the 610. 610 is a derivative of the 600. The 600 was the original product we did for you, and the 610 is a cost-reduced version of that in an outrageous package that's only 1.4 millimeters high, so it's really, really small. The main design objectives were low power consumption, high performance, outrageous packaging, and silly timescales. Okay, I don't know if you can see this. Over here is the ARM6 core, which Al has just been through, which we actually use as, this was an ASIC design, so we just take the ARM6 core and put it down. Along with that comes a 4 kilobyte cache. The cache design is slightly unusual. It's got 4 words in a line, and it's 64-way set associative. I sometimes ask Al, why was it 64-way set associative? And he says, because it got 10% more performance, Mike. So that's what we got. The other thing is the memory management unit, which on one level is a conventional Unix MMU. On another level, you asked for some wacky features, you got them. There's a write buffer. Because the cache is a write-through cache, you're still stuck with your main memory performance on writes. So the write buffer takes out that memory performance. And again, it's slightly unusual. It's got 2 address tags and 8 data words. And this is because, again, the ARM processor is very good at flagging sequential accesses. So things like store multiples are tagged with 1 address, and then there's lots of data. And so you can fill that FIFO as long as you only have 2 non-sequential addresses and up to 8 data items, and then the write buffer will stall. The clock block is also slightly unusual. We have 2 clocks, one for the cache control, the main processor clock, and the other is for the bus interface. Now, in a conventional design, those 2 clocks would be the same, and you would insert wait states into the fast clock when you're going to memory. And that's how you use the part, with M clock and F clock, the memory and the fast clock being synchronous. When we were in Acorn, we kept designing computers, and in the first few years, we'd go, oh, this clock is half that clock, or this clock's the same as that clock. We'll save an oscillator and tie them all together. And then 2 years down the line, we'd come back and go, we want to make the memory performance 20% better, and change the video clock by 30%. How do we do it? We're keeping the I/O speed at the same rate. So what we said in Acorn is we'd never tie 2 clocks together just because they happen to have the same frequency. And so the way we've always used this part and these clocks is to make those 2 clocks totally asynchronous. We've built systems with kind of a 25 megahertz cache clock and a 13 megahertz memory clock. Okay? Because that way you can tease the most out of the cheapest DRAMs you can buy. You don't have to wait until you come to the next frequency multiple, and you can insert or remove 1 more wait state. The downside is when you go off chip, you have to synchronize. So there's a latency penalty to pay every time you go off chip. So there's flexibility, but there's a hidden cost. You can choose which mode you operate the chip in. Then there's boundary scan, because we've put on all of our latest parts boundary scan for high volume test. And then there's an on-chip coprocessor which actually allows you to turn the cache on and off, selectively flush the TLB in the MMU, things like that. And then optionally on the outside of the 600 you can plug a hardware floating point unit. One of the things we did to make the 610 was to throw off that capability so we had fewer pins and it would fit into a smaller package. A very naive picture of a memory management unit. The point about conventional memory management units is they tend to tie together both translation and protection into the same block. And it's all driven from the level 1 and level 2 page tables. Now, you can use the ARM 600 in that mode and it would look like a familiar Unix memory management unit. But you've tied protection and translation together. And we were asked to do something that was slightly different from that. What we've done is separate out translation from protection and added a new thing on chip called the domain control register. Now this allows us to do several different things. On one level, the unit of translation is no longer the same size as the unit of protection. So in a conventional system, you'd have translation and protection all with a 4 kilobyte page. In this system, translation's on 4K boundaries, but protection is on 1K boundaries. Now, we were asked to provide 256 byte level of protection to do very efficient read and write barriers, but time pressure and silicon costs said no, we'll compromise and do 1K. And the way this works is you can take any level 2 page table chunk, which is kind of 1 megabyte of the memory space, and assign it to one of 16 different domains, prettily colored over here. When you do an access, you do a conventional check on the translation and the protection that comes from the page table entry. But then there's an additional check against the domain control register. Now, the domain control register is on chip, so you can access it in a single cycle. And what that allows you to do is put, say, filing system objects in a red domain and window manager objects in a green domain. If you then want to go off and garbage collect your red objects, and you want to temporarily make red objects invisible, you can take a single on-chip write, change the access permissions for all the red domains, do your garbage collect, and put it back. And so you don't have to go in and play with any of these page tables in main memory. You can do it all using the domain control register on chip. We were feeling generous and we kind of asked, what other things would you like us to put in this chip? We knew we were a RISC company, but we kind of offered the customer what he wants. And the software guys came back and said, whenever we go up and down linked lists, we're really bored with checking whether we've got to the end of a pointer. I said, okay. We'll see what we can do to help. Now, on the ARM, it's a byte word architecture. We never actually built, although in theory we could have done, misaligned word accesses. So what we offered was, we'll make a misaligned word access an exception. And if you want to turn that facility on, as long as the pointer at the end of your chain is a misaligned word address, you'll cause an exception. So you can throw the pointers around, and when somebody finally uses one that's at the end, you'll get an exception. You needn't do the test. I've never actually been back to ask whether you use it or not. Okay. One of the really important things on ARM, both in the core and a product like ARM 600 family, is power consumption. So we've done a lot of things in the cache design to actually minimize power consumption. So you start at the top left with your virtual address. That gets fed into the tag RAM, which on ARM 600 is in fact a CAM. And that'll select one word line of 4 words if it's in the cache. Doing that takes power. You've discharged the tags, you've discharged the data from the RAM. The data comes out and into the sense amps. Now you need sense amps to get high performance out of a memory system. The way sense amps work is they're basically analog devices. They watch the 2 plus and negative lines from your RAM change as they approach the final value. And what they do is they sense that transition, catch an intermediate value before you've hit the logic rail and go, we know what the answer is, it's a 1 or a 0. The downside with sense amps is they take a lot of power. In CMOS, non-threshold devices sit there and just burn current. So the first thing we do is make sure that this sense amp, when it's done its job, switches itself off. You don't wait till the end of the cycle, because that might be quite a long way away if someone's just turned the clock off on you. So it self-times and shuts itself down. Okay? So remember, you can stop the clock any time, any phase, any operation. So then you've got the data, and it's come out, and it's a conventional RAM system. Meanwhile, the processor's doing its next access. And being an ARM, it's already told you if it's sequential or not. Now, if it's sequential, you don't need to do the lookup in the CAM. So you don't pre-charge it, you don't discharge it, you just leave it as it is. It's still selecting a line in your data RAM, which you don't pre-charge, you don't discharge, you leave it as it is. The bit lines, the plus and the minus, have been hanging around for a long time now. They've actually reached their threshold values. So you don't need a sense amp, you just take an inverter off one of the bit lines, and it gives you the answer. So on sequential accesses, you don't use the sense amps. And in a RAM design, sense amps is where the power goes. We do similar sorts of things in the MMU. Again, you take the virtual address, you look it up in the CAM, comes across, and it gives you the protection and the translation. You need the protection in a hurry. So you take the protection through a sense amp, check it to see whether you want to abort the processor, and off you go. We've got a virtually addressed cache, so you don't need the translation. So the translation only runs off an inverter, and that's only used if you go off chip. So if you're not going off chip, you don't take any power. And again, if the access is sequential, you don't need to pre-charge this system, you just leave it discharged in the state it's in. Now, the MMU on an ARM 610 has a 32-entry TLB, it has hardware reload on misses, and it has selective flushing of that TLB. So you can say, if this virtual address is contained in the TLB, please remove the TLB entry. So that allows you to play with the page tables on a task swap, flush out those TLB entries that might now be invalid, and continue without having to flush the entire TLB. In summary, ARM 610 is a fully integrated processor with processor, cache, memory management unit, write buffer. And I guess it's got a depressingly large number of transistors for us, about 1/3 of a million. Most people like to stand up and say, our processor has over 1 million transistors. For us, that would be sort of an anathema. We really like to keep it down. It's still small, 8.5 by 8.4 millimeters. Power consumption's gone up from the core. It's 5 milliamps a megahertz, but we've got rather more to do in this system. Same sort of performance. Now, some people get confused. How come this is also 30K dry stones at 25 megahertz and the processor without a cache is 30K dry stones at 25 megahertz? Well, two reasons. Firstly, if you build an ARM 6 system and clock it at 25 megahertz, you have to provide a memory system that goes at 25 megahertz. That's expensive. So on an ARM 600, the cache is the memory system, that's going at 25 megahertz. You get exactly the same dry stones because dry stones fit remarkably well into caches of about 4 kilobytes. It's got extra hardware in the MMU for building entertaining operating systems. It comes in this outrageous TQFP package, which I've got some of if you want. I don't know, do you have After 8 mints here? Really thin mint chocolates? Well, they're about that thick. And you kind of, whenever I pick one up, I'm tempted to kind of go, how easy is it to break it? But we don't have enough yet to do that. I said silly timescales. We did the original ARM 600 in 9 months. So that was taking a microprocessor core that had a 26-bit address space. The original processor we thought was really neat, only had a 26-bit address, and the extra bits were used for the flags. So in a single register transfer, you could move the PC and the flags and save the state of the entire processor. However, we were asked to stretch this to 32 bits. For some reason, they seemed to think it was no big deal that you just made the PC bigger and the flags fell off the bottom and you put them somewhere else, and why did we not want to do this? But we did it. We built a new cache that was fully static and took no power. The original ARM 3 was dynamic and took power. I don't really know if you ever realized that, but that was a lot of work. And then we redesigned and cost reduced it to the 610 in another 3 months. Okay, I'd like to just go, yeah, we got time. Go over a few things about where we go in the future. Now, again, I guess I now have my marketing hat back on because what we have to have is a strategy. I'm not sure if technical people have strategies or not. Rule number 1, low-cost solutions. That's our business, is low-cost solutions. We're not interested in trying to build toasters like Deck Alpha and things like that. We're low-cost, low-power. Really important, low power. Now, we're doing some of the conventional things to reach low power. Low voltage processing, fairly straightforward, saves you a lot. We're doing more things to make sure our circuits don't clock when they don't have to, don't consume power. We're also doing a couple of things that are a little weird. One of them is we're trying to build a fully asynchronous ARM processor. So this processor has no clocks. You turn it on, it goes. On a hot day, it goes slowly. On a cold day, it goes fast. Has some interesting issues for kind of product design, marketing, sort of mine goes faster than yours. Why do we think it's a good idea? Well, we think it's a nice idea. We think it's a nice idea for several reasons. As you start doing big system design, things like clock skew and worrying about interface between blocks becomes really difficult. Now, with an asynchronous design technique, you have to handshake everything. So interfaces work across, skewing right across a big chip because they have to be fully asynchronous. There is no clock to skew to. So it allows you to do complex system design without really understanding the blocks you're putting together, which on one level is really neat and the other level sounds really dangerous. Another reason it's a good idea is it forces you to think about power consumption. In a synchronous design, you can kind of leave things clocking and they flail around in the wind and you don't really mind what they do. But if you think about it, you can gate clocks and you can minimize power. In asynchronous logic, you have to, from the start, say, I'd like this block to do this, and it gives you a handshake back saying, I've done it. And because it's event-driven, you're forced to think, I'll only fire off blocks when I've got something for them to do. And it becomes much clearer when you're actually asking the logic to do things. The final reason why we think it might save power is with synchronous designs, you're forced to design to your worst case. You decide you need 20 MIPS. 20 MIPS means you want a 20 megahertz processor. So you look at the core and you go, my critical path is in the ALU, it's the ripple chain on the adder. So you look at it and you think the worst case is when it ripples from the top to the bottom. So that's my critical path, I've got 50 nanoseconds. And you look at a straightforward adder, it don't go fast enough. So you add logic and you start putting in carry look ahead. And you put logic and logic and logic on the problem until you've got the critical path down to 50 nanoseconds. You go, phew, I've got a 20 meg part. You use it, and most of the time, the ripple goes halfway. So most of the time, you've got all this extra logic not doing anything except consuming power. With an asynchronous design, you can say, I want to design for the typical case. The typical case, the carry goes half the length, my critical path's half as bad, I'll do a logic design that runs at 50 nanoseconds with half the worst case ripple chain. Most of the time, that's what the ripple chain is, that's how fast the ALU goes. Every now and then you give it a difficult sum and it takes longer. You give it an easy sum and it goes faster. But typically, it goes at the speed you designed it for. But you've achieved that typical performance with less logic. Now, as I say, we think it's a nice idea. We're building silicon. We hope to have it in a year. When we get it back, we'll find out if it's a good idea or not. Something else we're quite happy to do, as we've shown to you, is actually changing the CPU. If you've got the volume, we'll give you a different CPU. It's as simple as that. Something else, higher performance. Whatever you say, you actually have to add more performance. Now, this isn't the slide I was going to show because it's got all the numbers on it. And Larry's a director of our company, and he's seen this slide, but even he didn't see the numbers. But I seem to have brought the one with the numbers on it. ARM 7700 is fairly simple. It's easy to see where to go from 600. You make the cache bigger, you take the geometry size down, and you clock it faster. It's easy. ARM 8, by the time we get there, you can't just keep playing the same game. You're on small geometries and you've got a big cache. What do you do next? Well, with ARM 8, we've actually got somewhere to go because if we want to by then, the cost of silicon might be cheap enough that we can go back and say, okay, we've got the ARM, we've got the instruction set. How about we add a branch prediction buffer? How about we make it a Harvard architecture? Let's increase the pipeline depth and chop up some of those critical paths. So when the people are doing things like the spark lightning have actually worked out which of these are good ideas, how well they work, we'll come up behind it when the research has been done by everyone else and go, they were the good ideas for building high-performance processors, and then we'll build one. So we're quite happy to kind of tag along a little bit behind everyone else, picking up the pieces. Something that's equally important for embedded control or low-power products is taking the power consumption down. So that was asynchronous logic, low voltage. They're the easy things. Three-level metal, well, you want small die, you go to more expensive manufacturing technology. In the middle, there's software ice. We're actually adding some of the things that you're probably used to on the Motorola parts that we don't have, like trace bits. We're putting debug support into the processor core. We're actually adding a whole new processor mode that allows you to run your remote debug interface that allowed you to split the C library between your host and your target in a separate mode, so you can protect that code against even your operating system code which you're trying to debug. So the aim is to have a processor that you can debug even when your privileged operating system code has gone bananas. Okay, the final thing we're doing is the ARM has a 2-tick Booth multiplier on it, okay, which means it takes between 2 and 17 cycles to do a multiplication. Now, that's just fine for low-grade DSP, and on the Archimedes products, that's used to do sound synthesis, plug-string algorithms, and fairly simple voice manipulation. If you want to do real DSP, then you need big, expensive multipliers. So we're looking at how do you build big, expensive multipliers. Okay, what does the silicon look like? Well, in the top right up here is an ARM6 core. Across the bottom is 4 kilobytes of cache. Down here are the CAM tags for the data. This is the 32 entry TLB for the MMU, and the stuff up here is the control logic, and that's the write buffer. And there's some more of the write buffer split down this end, and the JTAG tap controller. So there's not a lot of logic there. There's the core, the cache, an MMU, and just a little bit of control logic. That was made by GPS Semiconductors. This is a different color, so it's made by somebody else. This is actually made by VLSI Technology. So we have 2 real chips from 2 different manufacturers. And again, core in the top right, cache, CAMs, TLB, control logic. What's this? Oh, yes. This is Acorn originally. At Acorn, we originally designed 4 chips. The ARM, a memory controller that had yet another bizarre memory management unit with inverted page tables that always fitted on chip, so the cache was big enough to hold the entire translation space, and direct drive of DRAM, and a DMA controller for video. So there's the ARM. There is a memory management unit, and that's effectively the TLB that contains all the physical memory, control logic. A video controller that's a direct drive VGA display, and an I/O controller with interrupt mask and counter timers. And that's now all being put together on one chip, which you can put DRAM, ROM, and a monitor on the side, and you've got a single chip computer as long as you provide the memory. And finally, we're happy to take any questions. So if anyone has any questions. Yes?
I just want to say on the way out, if people go out the door over there, there's a demo of a soon-to-be-announced graphics package running both on an FX and also on an ARM card that's inserted into the FX. And you can see the relative speeds.
Thank you.
A word from our sponsor there.
Good, I like that. No difficult questions.
Uh-oh, no, I spotted something.
Yeah, here's a question. I don't know how difficult it is. What kind of competition are you looking at? I mean, you mentioned things like the Alpha or whatever, which obviously isn't designed for low power anytime soon. But presumably there are other things that are also looking at low power, like the AT&T CRISP thing, and you mentioned versions of Spark. What other processors are there out there?
Okay, the competition...
The question again, sorry. For the cameras, the audience at home.
Oh, fine. The question was, who do we think our competition is, if that's a quick rephrasing of it. Well, for the different products, that fits into different categories. For something like the ARM610, which is a complete microprocessor with cache and MMU, then in the low-power arena, I believe it'll be things like the CRISP, like the Spark Lite, like the 386s from AMD and Intel for low power. Now, the problems they have is if you actually look at their power consumption figures, they're low power compared to where they came from, but they're still high power parts. The other end is ARM6 as a macro cell used in embedded control applications. And there, what we're looking at what we like to do is take people who are in the 8-bit world thinking of moving to the 16-bit world, but are going to move all the way to 32 bits. And there's a whole load of Intel and Motorola chips out there that at the moment are the spectrum of different embedded control. I wouldn't pick any one of those out as being a particular competitor.
You originally designed to optimize for DRAM technologies, and you talk about your future directions. Have you thought about other memory technologies that are now under development, and what do you plan to do with those?
Right, I presume by that you mean things like the RAM bus and the very high-speed serial RAM interfaces.
All the various ones I think we're talking about.
Okay.
Sorry, no, I was just saying the question was the question was what are we designing for any of the newer RAM technologies? Not particularly that I know of. It's the ARM core is fairly simple. The interface is kept simple. There are no particular hooks put in there to drive any particular memory performance. As things mature, as memory technologies mature, we'll certainly keep track of that. And if there is an obvious way that we can enhance power, put something simple in to actually help boost the performance, we will do so. But at the moment, nothing is particularly planned.
Someone up the back. Yeah.
You showed earlier a little fragment of C code and the 4 instructions it generated. Who generated that? Your C compiler or by hand?
Okay, we had a little example of a piece of C code and assembler. Is it a cheat or not? I think that was handcrafted rather than the output from the compiler, but I don't know. Do you know?
I believe that was the output of somebody's mind, yes. But
that's an interesting compiler. Okay. I mean, I can stand here and say we think the compiler is really good and it makes really dense code, but without an example to back that up, next time around I'm going to have to get Lee to give me the compiled output. The compiler's good. I mean, as I say, it was first developed back in '85, so it's been optimized and tweaked for good ARM generation for coming up for 8 years. So I think we've got a lot of tricks in the compiler to make good code.
On that same piece of code, it looked like the equals case was not actually covered. There was a less than and greater than. That's why it looked
The equals case was covered by the branch. So it dropped through the 2 subtractions, and if neither of those subtractions was taken, it meant it was equal, which meant you'd drop through the branch.
As far as the less than, the else clause of the less than should have been greater than equal, and it was a greater than.
sorry, there was.
Yep.
You said it was a little painful moving up to 32-bit. How do you view the move to 64-bit?
Okay, the question, moving from 26 to 32 is painful. How do you feel about moving to 64? Well, the simple answer is, Al's the architect, he could answer that.
It's the marketing manager who will answer that.
I think at the moment, I'm not really concerned about the move to 64 bits. In the market we're in, 64 bits just isn't appropriate. Again, we're not in the PowerPC world. We're not talking about very high performance desktop machines. If you want to ask me when do I think my radio telephone and my little organizer needs 64 bits, I hope it's not for a very long time.
Question is, are your interrupts random?
Are our interrupts re-entrant?
You have to save stuff on the stack. The example I showed you was for the fast interrupt. There are actually two interrupts, a fast and a normal level. The fast interrupt is really for the maximum 1 microsecond getting there time. And the idea is you don't have to save stuff on the stack. You normally only attach a single interrupt at a time to that, so you didn't have to go around looking to see whether the interrupt source was generated. You just do it. Other interrupts would all be ganged through the normal interrupt request, and the first thing you'd have to do is to save away some state to the stack.
On entry to both IRC and FIC, those interrupts are disabled, so you can save your state on the stack if you want to make it re-entrant.
Yeah, when people look at VLSI getting denser and denser and being able to fit more and more things onto a chip, one of the things they look at is the possibility of having more than one CPU on the chip. And given that your CPU at the moment takes up a fairly small percentage of the chip, I wonder if that's something you're looking at.
Okay, the question was, as die sizes get, or as silicon densities go up, what would we do about multiprocessing? Okay, yes, we have thought about that, and there are some entertaining ideas we have at the moment on how to put 2 CPUs on with 3 caches and 2 MMUs, and the idea goes you have 2 data caches, you have 2 instruction caches and 1 unified data cache. Now, I think we've got a little bit of time to go before those sizes actually make a die, but yes, once you can build that amount of RAM technology, popping another processor core on is going to be real easy.
You have fast interrupts. Do you also have fast traps for things like high-level interpreter instructions?
Do we have fast software traps? Yes, there's a software interrupt which takes you through a vector in low memory into supervisor code, into a privileged mode at a known vector.
And there's 24 bits at the bottom of the instruction itself. There's the 4-bit conditional code, a 4-bit field which defines it as a software interrupt or SWI instruction, and the rest of it is yours to put a number in there. When the operating system receives it, it can look at that number, decode it, and jump off to some appropriate routine.
Okay, the other thing we can do is there's a set of coprocessor instructions whose format is defined but whose semantics aren't, and we've defined the semantics for a floating point accelerator. And the idea there is if you have the hardware, the floating point accelerator tracks the instruction pipeline. If the instruction is executed, the ARM says, I want you to do this instruction, which you've now been modeling in your pipeline, and then there's handshake backs to say, thank you, I've done it, or I'm thinking about it. And if that hardware isn't there, then you'll take a software trap and you'll find yourself going through a different vector for an undefined instruction trap, which means you can build a floating point emulation in software and with the same object code for the customer, run it with either floating point emulator or hardware. And it's one of those coprocessors that you can have 16 of them. We use one of them for the on-chip manipulation of the registers. So you don't have to, you can expand the instruction space to say coprocessor 15, if you do this CPRT to it, it'll turn the cache on, and this one will turn it off, DO. But yeah. Question at the back. No, sorry, yes, you're near the back.
Right. Do you have a floating point processor right now?
Right. The question is, do we have a floating point coprocessor? What we have at the moment, okay, this is fun, is a hardware floating point solution based on, and yeah, once again we picked an entertaining chip, the Western Electric
206.
Yes. And so we have that chip and a little ASIC that turns its bus interface to look like an ARM bus. Now, the reason we did that was the man that invented the instruction set also said floating point shall be 80-bit. So the FPE was written as 80-bit, and when we looked around for a hardware solution for 80-bit floating point, and this was about 4 or 5 years ago, that was one of the very few 80-bit floating point accelerators that you could actually buy. Well, we thought we could buy it. That processor family hasn't proved very successful, and that silicon is not exactly very easy to come by. At the moment, we have under development our own floating point accelerator, which again is a RISC-based development. Most of it's done in software, and the tricky bits are done in the easy bits are done in hardware, and the tricky bits are done in software. So come the end of this year, we'll have our own floating point hardware. Yes?
The floating point, is that IEEE compatible?
The floating point is IEEE 80-bit. Okay, thank you very much.
Thank you.